Okay, so we were discussing about cyclic subgroups, right? Yeah. So let's continue our discussion. So this is the second lecture on cyclic groups, right? Okay. Yeah. So let us prove a very important proposition over elements generating cyclic groups. This is kind of pretty relevant to the things which we had discussed in the previous lecture. Okay, let us first quickly recall what we have studied in the previous lecture. Then I guess it will be a sort of a warm for us. Yeah, so we had discussed that H, suppose H is the cyclic group generated by X, then this group is certainly of the form x to the power n, where n are elements in the integer. Now from here we have two very important structure. One is if the order of x is some finite number n, then the subgroup is basically the elements 1 x x squared, so on and so forth till x to the power n minus 1, right? One thing which I had not discussed in the previous lecture about this structure of the cyclic subgroup generated by an element of finite order is that, yeah, we had discussed that we cannot extend beyond the power to n minus 1, and these are the only distinct elements for the set. We had not yet discussed about the inverse elements, right? But if you carefully observe that if you choose any element from here, say you choose x squared, then if x to the power a is the inverse of 2, then this must equal 1, but that would mean x to the power a plus 2 equals 1, but that would mean a plus 2 equals n precisely, but that would mean a is equals to n minus 2, and x to the power n minus 2 is indeed an element in this set itself. So there is no question of the inverse elements, right? It's quite obvious from here. What if the order of element is infinite, infinite? Then this is the indeed the structure. So you start with the element x, you keep on composing it with itself, and you can also think of keep on composing the inverse of that element. Okay. We have said that we also want to discuss about what the subgroups of a cyclic group looks like. So to do that, first let us talk about what are the possible generators of a cyclic group. Okay. And to do that, we require a certain proposition. The proposition is as follows: that let G be a group, and we choose a non-zero integer. Let's say, yeah, a non-zero integer will do. Then number one is that if order of x is infinite, then so is order of x to the power a. Number two is the important one. So let me just give a star here. If order of x is n, then the order of x to the power a is n upon the GCD of n and a. Okay. So these are the two things which we want to prove now, and the later things which we want to discuss will follow up from here only. Okay. So let's prove this out. Proof of one is fairly simple, right? Because suppose x to the power a has a finite order. That is, suppose the order of x to the power a is m, then by definition x to the power a m must be equals to 1. But x cannot have a finite order. This means that x must have a finite order. So it's a contradiction. You can structure as this on your own. There is nothing too complicated in it. Number two is a bit tedious, but not that. You can think of it in your own way. I'm giving out a certain proof. Okay, this is x. Okay. So what we first do is that we choose a notation for the GCD. Okay. So let D be the GCD of n and a. Okay. Clear. So we are to typically show that the order of x to the power a is n upon d. Okay. We need to simplify this a bit. How do we do that? Observe that. Observe that. If d is the GCD of n and a, then this implies d divides n, and D divides A. This is directly from the definition of a GCD. But this implies that you can write N as D times B, and you can write A as say D times C. Okay, right? So if N can be written as D times B, then so this typically implies N upon D is B, right? So if you choose let x to the power A be y, so in a way it suffices to show that the order of y is B. Okay. Now, what can be the the procedure which we can follow? One thing which we can do is that we show y to the power b is 1, and we show there is no smaller integer to happen. So that can be one procedure. One procedure can be that we show that the if order of y, so one procedure I guess you people have understood. One more thing which we can do is that we can show that the order of y divides b and b divides back order of y. Okay, we tend to follow this procedure because there is some sort of divisibility going on in our proof. Okay, you can also check and prove in the other procedure that y to the power b is 1. Now y to the power b is 1, that's quite trivial. We will show it obviously, because observe that what is y to the power b? So by definition is x to the power ab, right? Now what is b? B is n upon d, right? B is n upon d. So this is or rather we can write a as dc. Let's a be written as dc. So we are actually not ignoring the division notation. So a is dc, so this is dcb. All of the elements dc and b are integers, so they will obviously commute. So we can write it as, now what is so yeah, so we can write it as dbc, right? But what is db? Db is n, so this is x to the power n whole to the power c. What is x to the power n? The order of x is n, so it's 1. So y to the power b is indeed 1. So this is obvious. Now I'll obviously follow this procedure, but you can obviously try to show that there is no smaller integer than b which obeys this property. Obviously use the fact that the smallest integer for x such that x to the power of that integer is 1 is n. You can obviously you should use that. You will need to use that as well. Okay, so we continue the proof here. Yeah, so we have y to the power b is 1. Now in the previous lecture we had shown that order, if order of an element is k and x to the power some m is 1, then k will divide m, right? So if y to the power b is 1, since y to the power b is 1, that implies that the order of y divides b. Okay, so this is clear. We need to show that b divides back the order of y. Okay, so let the order of y be k. Okay, let the order of y be k. Okay, so if order of y is k, then that immediately means x to the power a k is 1. Okay, now order of x is n. Okay, since the order of x is n, then by this same procedure we can show, we say that n divides ak, right? I hope this part is clear. Okay, now a is dc and n is db, so this implies that db divides dck. Okay, okay, now one more thing I should already have stated it here, is that since d is the GCD of n and a, and n can be written as d times b and a can be written as d times c, so they cannot have any common divisor except d, or I should say that b and c are co-prime. I should not use the term that they cannot have a common divisor other than d, because d is the greatest common divisor by definition. I shouldn't have used that term. It was just a a mispronunciation of what I wanted to say. But the fact is b and c are co-prime, right? B and c are co-prime, right? So this is the least reducible form in a way, which I want to say. So if B and C are co-prime, so this implies B must divide CK, because D will eventually cancel out. D is obviously non-zero. But B and C are co-prime, so this implies B cannot divide C, but B cannot divide C as they are co-prime. So this implies B must divide K. K was the order of Y. B was the order of Y. So this implies B divides the order of Y. Yeah. So we have shown that the order of Y divides B. We have the B divides the order of Y. Hence they must be the same. Right? Okay. So this was a fine statement. Now observe. So if the order of X is N, then order of X to the power A is N upon the GCD of N and A. What if A and N are co-prime? Therefore, if N and A are co-prime, then the order of X to the power A is indeed N itself, while N is the order of X as well. Therefore, if X is the generator of some cyclic subgroup, so is X to the power A. I guess it's now obvious. Therefore, if H is the cyclic group generated by X and A is a non-zero positive integer, a non-zero integer such that N and A are co-prime, then H is also generated by X to the power A, right? Okay, let's now choose. Okay, let us consider an example. Consider Z12. Okay, obviously Z12 is a additive group and the operation is addition modulo 12, right? So it's an additive group with addition modulo 12. What are the generators of Z12? One is indeed a generator, right? So let's write it as, yeah. So one is indeed a generator. But my question is, what are the other generators? Okay, what are the other generators? Now observe, this is an additive group. So X to the power A in this case is equivalent to saying AX, right? What is 3? 3 is 3 times 1. The order of 1 is 12, right? No, sorry. I'm very sorry. The order of am I doing something wrong here? Precisely. Yeah. Will 1 generate? Yeah, it will do. Correct. Okay. Correct. Yeah. So 1 generates Z12. Obviously, 1 generates Z12. What are the other generators? Yeah, that was my question. What are the other generators of Z12? Okay. Clear? Okay. Let's check it out. So if I relate this to what we have said here, then order of X is, what is the order of 1 in Z12? What is the order of 1 in Z12? It's 12, right? Because 12 times 1 is 0 modulo 12, right? Right, yeah. The identity in Z12 is 0, correct? Okay. So, okay. Yeah, I think I'm getting it all right, correct? What are the other generators? So order of X is 12, right? What is the order of 3? What is the order of 3? Yeah, so the order of 3 will be 4. This won't work. Even numbers won't work, obviously. What is the order of 5? Clearly the order of 1 is 12, right? So clearly the order of 5 will be 12, right? The order of 5 will be 12, and this immediately comes out from the fact that 5 is nothing but 5 times 1, right? So if I consider 5 to be of the form some X to the power A, so it's so this is the A indeed, and A and the order of N, which is order of 1, which is 12, is 1. So 5 will also generate Z12, right? This implies that Z12 will also be generated by 5. Will it also be generated by 7? Indeed, right? It will also be generated by 12, by 7. Observe that Z12 will also be generated by 7. What is the reason behind that? Because Z is in the form Z times 1, order of 1 is 12, Z and 12 are co-prime, right? Indeed. It will also be generated by 11 because 11 is equals to 11 times 1. Order of 1 is 12. 11 and 12 are co-prime, right? Okay. So the generators of Z12 are 1, 5, 7 and 11. Aren't these the only numbers below 12 which are co-prime to 12, right? Which are co-prime to 12? Correct. This brings us to one very important proposition. Okay. So this can be thought of as a corollary as well, proposition. So the proposition is of this sort. Let H be the element, the subgroup generated by X. Number one, if X is the order of X is, if the order of X is infinite, then H can be generated by X to the power A if and only if A is equals to plus minus 1, right? This statement is quite obvious because A cannot be, brought to any other power and yet generate H. Okay, you can check this as an exercise. Obviously, this comes out as a corollary of what we proved. Okay, clear. Number two. Number two is that now this is indeed the fact because X to the power A will also have infinite order, right? X to the power A will also have infinite order because the order of X is infinite. That's it. Number two is that if order of X is n, which is finite, then H will also be generated by X to the power A if and only if A and n are co-prime. This also comes out as the as the second statement in the previous proposition. Right? The obvious thing to observe from here is that X to the power A generates H, which is equals to this, if and only if A and n are co-prime. So that means if I collect all those elements which are co-prime to the order of X, X to the power of those elements will be the generator of H. So can I say that the number of generators of H is indeed phi of n, the Euler-Taussian function, the Euler-Taussian function. This gives you the number of elements co-prime to n, if you recall. N is obviously the order of X, right? So this is a very important counting theorem. I shouldn't use the term counting theorem, but a very important tool to calculate the number of generators of a finite cyclic group. Clear? Phi of n, how to calculate phi of n? Let me just give it out. So suppose n has a prime factorization p1 to the power a1, p2 to the power a2 till pn to the power pm to the power am. So this is the prime factorization of n. Prime factorization of n. Then phi of n is calculated as n times 1 minus 1 by p1 times 1 minus 1 by p2, so on and so forth, till 1 minus 1 upon p. Okay, this gives the number of co-prime elements, less than n. Okay, and this indeed gives you the number of generators. I guess this concept is now clear. Okay. Okay. The next important proposition for cyclic groups, and this will be the last proposition of our discussion in cyclic groups, is the following. I don't want to write as a proposition because it is a much stronger statement. So let me write as a theorem. Okay. The theorem says that let H be the cyclic group generated by X. Number one, every subgroup of H is cyclic. Okay, every subgroup of H is cyclic. This obviously follows from your intuition, but what can we say more? Okay, what can we say about the generator of this subgroup of H? Okay, so specifically, like whenever you say the term cyclic group, you should always be concerned about what is that cyclic group is being generated with, right? So specifically, either if K is the subgroup of H, then there are only two possibilities for K. Then either K is the trivial group, or K is generated by some x to the power A. Let me use the term x to the power D, because A is used rigorously in the previous statements. So K is equal to x to the power D, where D is the smallest positive integer. D is the smallest positive integer such that x to the power D is in K. Okay. Number two is that if the order of H is infinite, that is indeed telling that the order of X is infinite, then for all A not equal to B, let these be elements positive integers other than 0, then the cyclic group generated by A cannot be equal to the cyclic group generated by B. Okay. Furthermore, the cyclic group generated by x to the power m indeed is equal to the cyclic group generated by x to the power mod of m. Clear? Now we have a stronger statement than this, than two, or I shouldn't use the term stronger statement, but I should use the term a structurally similar statement. That is, the proof of 3 is kind of structurally same for the proof of 2. Okay. So the proof of 3 is somewhat of this sort, that the if n is the cardinality of H, then for all A in Z plus, that is the positive integers, such that A divides n, then there exists a unique subgroup. There exists a unique subgroup of order A, which is which I can state as, so it's x to the power D, such that D is the quotient when A is divided by n. Sorry, when n is divided by A. Okay. This can be also expanded to say that for all integers m, the cyclic group generated by m equal to the cyclic group generated by nm. Okay, where n is the order of x. Okay, so these are the statements which are quite important to observe. Okay, we prove 1, we don't prove 2 and 3. I'll just give a hint to 3. 2 is left as an exercise. Okay, so we prove 1. Okay, proof of 1 is you can think of it a bit, but I don't think it's that complicated a proof. If K is 1, it's trivial, right? If K is 1, it's trivial. So let K be not the trivial group. Okay. Then obviously if K is not 1, then there exists some A such that A is x to the power A is in K. Okay. Now if x to the power A is in K, then that immediately means x to the power minus A is also in K, because K is a subgroup. K is a subgroup. If x to the power A is in K, then the inverse of x to the power K, which is exactly equal to x to the power minus A, that is also in K. Okay. Now, what can be the procedure you can think of to show that we can consider some smallest element of the form x to the power d which is in K, provided there is some positive integer a such that x to the power a is in K. So the obvious approach will be, these are integers, right? We are working with positive integers, right? So the obvious approach will be the well ordering principle. The well ordering principle of natural numbers, right? That will be the obvious approach to find out some smallest element. Okay. So what we do is that we consider a set. So let S be the collection of elements B such that B is a positive integer and x to the power B is in K. Okay. Then this is a subset of natural numbers. Therefore, by well ordering principle, there exists some smallest element in S. We denote this element as D. Say D such that x to the power D is in K. So D is the smallest positive integer such that x to the power D is in K. Right? Right? Okay. Now, since x to the power D is in K, so every, whenever you are composing any element with x to the power D, from elements inside K, then, so sorry, from elements inside the, rather, whatever I'm trying to say is that the cyclic group generated by x to the power D is a subgroup of K, right? Because whenever you choose two elements from x to the power D, okay, say x to the power D1, x to the power D2, if you compose them back, they're elements inside x to the power D, but they are indeed elements inside K as well because K is a subgroup. So this is obvious, right? So what can I say about the reverse inclusion? Okay. What we do is that let us divide an arbitrary positive integer a by d. So we have a as qd plus r. I'm not specifying how r behaves because that is obvious from the Euclid's division lemma. Okay. So that implies a minus qd is equal to r. A is an element from S. Okay. A is an element from S. A is an element from S. That is x to the power a is in K. So this implies x to the power a times x to the power d to the power minus q is equal to x to the power r. This is obvious. But x to the power a is in K because a is an element from S. X to the power d is in K. That's also given. So this implies the left hand side is in K, but that implies x to the power r is in K. But r is less than d, right? If non-zero, contradicting. So let me just, if r is non-zero, then this contradicts the minimality of d. This contradicts the minimality of d. Therefore, r needs to be 0. This implies d indeed divides a, right? So what does that mean? So any element you choose out of K, the power of that element is some multiple of d. So that element is indeed inside the cyclic group generated by x to the power d. So that implies K is contained in x to the power d, the cyclic group generated by x to the power d. So that implies K must be exactly equal to x to the power d. That is what we wanted to prove, right? Clear? Okay. Okay. Now let us move on to the proof of the. I will not give the proof. I'll give this as the structure of it. Okay. Okay. So no, let me leave it as a proof. Leave it as an exercise. 2 and 3 are left as an exercise. I guess you can easily prove it. Are left as an exercise. Try on proving it. If you can't do the proofs, then please leave a comment under this lecture. Then I'll prove it in the next lecture. Okay, both these statements 2 and 3. Okay, there is nothing too complicated in it. Just use the proposition we proved in the just before this theorem. Okay, clear? Okay. One more observation. Let me just state out one more observation. What can we say about cyclic groups in Z mod NZ? About the inclusion of cyclic groups in Z mod NZ? So, question: uh, consider the group Z mod NZ. I'll give the answer to it. Try to verify it. Try to justify it. Consider the group Z mod NZ. I claim that any cyclic group generated by an element A will be contained in a cyclic group generated by an element B if and only if the GCD of B and N divides the GCD of A and N. Okay, clear? How can you extend this? Extend this to Z. So obviously in Z what will happen? So in Z it's typically N is equals to 1. So in Z, if A is contained in B, then B must divide A. Okay, try to verify this on your own. Okay, this is also not a very complicated proof. So this immediately comes out from how the what is the structure of the cyclic group generated by B and what is the structure of the cyclic group generated by A. Try to use the fact that if the cyclic group generated by A is contained in the cyclic group generated by B, then A must be an element of the cyclic group generated by B. It will obviously follow up from here, and also keep in mind that this is an additive group. So is Z. Okay, clear? Okay. Okay, so we leave this lecture here. In the next lecture, we will be starting from the concepts of quotient groups. Quotient groups. Okay, so meet you guys in the next lecture.